For problem 1, we want to find the value of k so that the function f of x is continuous on the entire real line. The only x value we need to concern ourselves with is -1. That's where this change happens in the function. So for this function to be continuous, it's enough to make sure that the limit as we approach -1 exists. This is the same thing as saying the limit from the left of the function has to be equal to the limit from the right at -1. So we want that the limit as x approaches -1 from the left of f of x is equal to the limit as x approaches -1 from the right. If those are the same, the limit at -1 will exist and this function will be continuous. Well, if we approach -1 from the left, we're using this portion of the definition. So in place of f of x, I can substitute k times x cubed minus 5. So on the left side, we have this is the limit as x approaches -1 from the left, really of some constant k times x cubed minus 5. Likewise, the limit as we approach -1 from the right depends on this portion of the definition. I'll replace f of x with k minus 3x. So this is the limit as x approaches -1 from the right of k minus 3x. So we want these two things to be equal, and k is a number. It's a constant. We can evaluate this limit by simply putting -1 in place of x, and we can do the same thing on this side as well. We're going to put -1 in place of x. In doing so, we've evaluated the limit. On the left, we have k times -1 cubed minus 5 is equal to, on the right, we have k minus 3 times -1. We just want to choose the value of k that makes this a true statement. So over here we have -1 cubed is -1, so this is negative k, then minus 5. And on the right we have k, well that minus and minus will be a plus, and so we'll have plus 3. I think I'll subtract 3 from both sides and add k to both sides. So I get -8 is equal to 2k. And after I divide both sides by 2, I get that -4 is equal to k. So k equaling -4 is the value that is going to make the limit from the left equal the limit from the right. This means the limit at -1 does in fact exist and is actually equal to the function there, and so our function is continuous on the entire real line. In problem 2, we will evaluate a few limits, starting with this one here in part A. What is the limit as x approaches 3 of x squared plus x minus 12, all divided by x squared minus x minus 6? Maybe we can just simply put 3 in place of all the x's and simplify this to get our answer. If you try this in the denominator, you get 3 squared is 9, minus 3 minus 6 is 0. So this approach will not work. However, this limit may still exist. Perhaps we can factor the numerator and the denominator and cancel a common factor. That is the approach that I'm going to take. This is equal to the limit as x approaches 3 of, I'll start with the denominator. Can we factor this into two pieces? It looks like it is x minus 3 times x plus 2. And in the numerator, we have x minus 3x plus 4. So I'm seeing that there, in fact, is this common factor of x minus 3 that can be canceled. So the limit that we started with is equal to the limit as x approaches 3 of, really it's just x plus 4 divided by x plus 2. I don't need the parentheses anymore because nothing is really being multiplied together. So this limit is equal to this limit. Now to solve this limit, can we simply just substitute 3 in place of x to get our answer? And the answer is yes. This is a rational function which is defined at 3. So by direct substitution, we can say that this limit is equal to 3 plus 4 divided by 3 plus 2, which simplifies to 7 over 5. And that is the completely simplified answer, and it's equal to the limit that we started with. In part B, we want to find the limit as h goes to 0 of quantity h minus 1 squared minus 1 all divided by h. Again, we cannot put 0 directly in place of h to get our answer because we'll be dividing by 0. So what I'll do is simplify this expression. Maybe we can cancel the factor of h. To start with, I'm going to expand the h minus 1 squared. This is equal to the limit as h goes to 0 of h minus 1 squared is, well, you square the first term and you square the last term, but you get minus 2h as your middle term. Then there is a minus 1 that is still there, and this is all divided by h. So just a quick off to the side here, h minus 1 squared means h minus 1 times h minus 1. We have to distribute to multiply this out. We have h times h, which gives us h squared. H times minus 1 gives us a minus h. Minus 1 times h gives us a second minus h. That's why there's a minus 2h. And lastly, negative 1 times negative 1 is positive 1. That all being said, when we look at this expression, we can now simplify by subtracting this 1 from this positive 1. This is equal to the limit as h goes to 0 of, okay, so we have h squared minus 2h all over h. We can eventually cancel this h by factoring an h out from both terms in the numerator. Over here, I'll write that as the limit as h goes to 0 of, the denominator is h, and if you factor h out from both terms in the numerator, you have h minus 2 that is left over. You can think backwards. If you distribute this h to both terms, you'll get an h squared and a minus 2h. It's at this point where you can cancel the h's, and this is equal to the limit as h goes to 0 of simply h minus 2. If we directly substitute 0 in place of h, we get minus 2, and that is our answer. In part C, we want to figure out the limit as t goes to 5 of 3 minus the square root of t plus 4, all divided by t minus 5. Again, we cannot directly substitute 5 in place of t. The denominator is 0, and actually the numerator is 0 too. Now, there is a trick for this problem. If you see a sum or a difference with something and a square root, you can multiply by something that's called the conjugate that will make it simplify very nicely. The trick goes like this. If you take this limit and you multiply it by 1, it won't change the value of the limit. I don't really think that step is absolutely necessary. You can just start here if you would like. I'm going to take this expression, so it's 3 minus the square root of t plus 4 divided by t minus 5. Instead of writing it as 1, I'm going to set this up as a giant fraction. And I'm going to take this minus sign and make it a plus sign, and take that entire thing and write it right here. That is 3 plus the square root of t plus 4. When you multiply these two numerators together, it'll simplify nicely by canceling the square roots. Now, if you want this fraction to really be equal to 1, you have to divide by the same thing that is in the numerator, so I'll divide by 3 plus the square root of t plus 4 as well. I'll put parentheses around this t minus 5. Ultimately, notice that we're approaching 5. I'm going to want to cancel this t minus 5. It's the thing that's making the denominator 0. So I'm not actually going to distribute these two terms together. I'm going to leave them factored. But in the numerator, I will distribute. I'll go 3 to 3, 3 to this positive square root. Then I'll take this term and distribute that in as well. Let's write that whole thing out. This is the limit as t goes to 5. And I'll first write the denominator, only because we're not multiplying it out. We're just saying it's t minus 5, which I'm hoping cancels, times 3 plus the square root of t plus 4. In the top, we have 3 times 3, which is 9. Next, we have 3 times this positive square root, which there's not much to simplify. I'll just put 3 times the square root of t plus 4. We now multiply this in with the negative, so we get negative 3 times the square root of t plus 4. I have to extend my fraction. If you'd like, you can put this after the plus 4, just so we're not confusing what we're taking the square root of. And lastly, I'm going to take this thing and multiply it to this, which is, well, it's going to be negative because we have a positive times a negative, so I'll put negative. And it is the square root of t plus 4 times the square root of t plus 4. That's the same thing as squaring the square root of t plus 4. And what does that equal? T plus 4. It is important to put parentheses around it because this negative is multiplied to this entire thing. In fact, we'll have to distribute it in a little bit. There's a lot of writing here, but the important thing to point out is that these middle terms are equal and opposite. They're going to cancel to give us 0. That will always happen when you multiply by the conjugate. Also, the square roots are completely gone. I'm going to rewrite this as the limit as t approaches 5 of, so that's 9 minus t plus 4, all divided by t minus 5 times 3 plus the square root of t plus 4. And if you distribute in that negative, I'll put that as my next step here. This is the limit as t approaches 5 of, well, that's really 9 minus t minus 4, all divided by t minus 5 times 3 plus the square root of t plus 4. And I'm going to subtract the 4 from this, and I get 5 minus t, which is really close to t minus 5. So I'll continue that next. This is the limit as t goes to 5 of 5 minus t divided by t minus 5 times 3 plus the square root of t plus 4. Now, it'd be great if this factor completely canceled with this factor, but they're not exactly the same. For emphasis, I'll put some parentheses around it. The thing to point out is, which I'll write above here in red, if you factor out a negative from 5 minus t, you get negative 5 plus t, because if you multiply the negative back in, it'd be positive 5, then minus t. Or, written another way, this is negative times, instead of negative 5 plus t, I'll put t minus 5. So if you see that, well, these are almost the same, but they're backwards, you can factor out a negative and then put t minus 5 in this case. I'll put that as my next step on the next slide, replacing this with this. So that was the limit as t approaches 5 of, so I'll put negative t minus 5 divided by t minus 5 times the quantity 3 plus the square root of t plus 4. Because now we can cancel this t minus 5 with this t minus 5. There is a negative 1 that is left over in the numerator, but we have the limit as t approaches 5 of, so that's negative 1. I don't need the parentheses on this part anymore because this is gone. I'll just put 3 plus the square root of t plus 4. If we can now directly substitute 5 in place of this t and get an answer, that will be the value of the limit. And we can. We're not going to divide by 0. We'll get an actual value. So I'll put 5 right there. This limit is equal to negative 1 divided by 3 plus the square root of 5 plus 4, which is really negative 1 over, we can just put the negative in front of the whole fraction. That's 3 plus the square root of 9, which is negative 1 over, well, that's really 3 plus 3, and we have our answer of negative 1 over 6. In problem 3, we're given that f of x is equal to x to the 4th minus 3x cubed plus 1. We're going to show that f of x equals 0 has a solution in this interval. That means it has a root or a 0 between negative 1 and positive 1. Now we want to make sure that we use an appropriate theorem in explaining our answer. That theorem is the intermediate value theorem. It says that if you have a continuous function on an interval that goes from negative to positive, at some point within the interval, it must equal 0. So that means we're not actually going to find an exact value for x. We're just going to use a theorem to show that there must be one. So the first thing is, we need to know that this function is continuous on this interval. And is it? Yes. The reason is this is a polynomial. So it's important that we state that. I'll say that f of x is continuous on the interval from negative 1 to positive 1. as it is a polynomial. Polynomials are continuous everywhere, and therefore they're going to be continuous on any interval that you're working on. Okay, the next thing we're going to do is check the endpoints of the interval in this function. I'm hoping that we get a positive number for one and a negative number for the other. So next, I'll note that, all right, f of -1 is equal to -1 to the fourth minus 3 -1 cubed plus 1. This is 1 plus 3 plus 1, which is 5. And that is a positive number. And f of 1, the other endpoint of the interval, is 1 to the fourth minus 3 times 1 cubed plus 1. That's 1 minus 3, that's -2, plus 1 is -1. So we have that the function goes from a positive number to a negative number on the interval from -1 to +1. More explicitly, -1, which is f of 1, it's less than 0, is going to be less than 5, which is f of -1. So let's actually state that. I'll say as f of 1 is less than 0 is less than f of -1, right? This is -1 is less than 0 is less than 5. As this is true, I can say by the intermediate value theorem, there exists a number c in the interval from -1 to +1. It won't be the endpoints. It has to be within the interval, such that the function evaluated at this number is equal to 0. Now, what is this number? I have absolutely no idea, but we did actually do what the question asked. We found that there must be some number within this interval such that this equation is true. In problem 4, we're given that f of x is equal to -2x minus 4, and g of x is equal to x to the fourth plus 2x minus 1. If we assume that near x equals -1, there's a function h that satisfies this inequality, that is, f of x is less than or equal to the function h of x is less than or equal to g of x, can we figure out what the limit as x approaches -1 is, even though we don't have a formula for it? There is a theorem that will help us do this, and it's called the squeeze theorem. What I'll do is state the hypotheses that we need for the squeeze theorem, and then we'll figure out what this limit is equal to. So first of all, let's look at the limit as x approaches -1 of the function f of x. Now, what is this equal to? Since the function f of x is equal to -2x minus 4, which is a line, by direct substitution, we can put -1 in place of x to figure out the value of the limit. It's this. -2 times -1 minus 4. This is equal to -2. Also, we'll look at the limit as x approaches -1 of the function g of x, which is the limit as x approaches -1 of x to the fourth plus 2x minus 1. Again, here we have a polynomial, so by direct substitution, this limit is equal to -1 to the fourth plus 2 times -1 minus 1. That's also equal to -2. So we now have that f approaches -2 and g approaches -2. So this is going to -2, and this is going to -2 as we approach -1. Since h is always between these two functions as we're near -1, that means this limit has to be equal to -2 as well. This only works because these two numbers are the same. So to complete this, what I'll state is, as f of x is less than or equal to h of x is less than or equal to g of x, By the squeeze theorem, the limit as x approaches -1 of h of x must be equal to -2 as well. In problem 5, we're going to find all horizontal and vertical asymptotes of the given functions. And if they don't exist, we'll explain why. Let's start with f of x. If we're looking to find the vertical asymptotes, in this case of a rational function, what we can do is check to see where the denominator is equal to 0, and at the same time, the numerator is not equal to 0. So when does this happen? Well, what I'll first do is say, when is x squared minus 16 equal to 0? And that's the denominator. Or simply, when is x squared equal 16? Well, that's when x is equal to plus or minus 4. If the numerator is not 0 at plus and minus 4, that means there are vertical asymptotes at these two x values. So we're going to check x equals plus and minus 4 in the numerator. So that is 3 times -4 plus 4. That is -12 plus 4. That's -8. And this is non-zero. Likewise, 3 times 4 plus 4. That is 12 plus 4. That is 16. This is also not 0. So in a rational function, non-zero over 0 means there must be a vertical asymptote at these given x values. So I'll state that x equals -4 and x is equal to +4 are vertical asymptotes. Because these numbers make the denominator 0 and the numerator non-zero. And that's it. Next, we'll check to see if this function has any horizontal asymptotes. The way we'll do this is by using limits at infinity. I'll put this on the next slide. For horizontal asymptotes, we're going to look at the limit as x approaches either positive or negative infinity in the function f of x. The nice thing is, for this rational function, it'll be the same limit for both, whether you use positive or negative infinity. So I'm just going to leave that plus or minus in front of this infinity symbol as we work through this argument. So this is the limit as x approaches plus or minus infinity of, the function was 3x plus 4 divided by x squared minus 16. What we'll do here is divide every single term by the largest power of x, which is x squared. This is equal to the limit as x goes to plus or minus infinity of, so this is 3x over x squared plus 4 over x squared divided by x squared over x squared minus 16 over x squared. So these two limits are equivalent. Now I'll simplify. This is going to be equal to 1. Nothing cancels here or here, and I can cancel one factor of x over here. So this limit becomes the limit as x goes to plus or minus infinity of, so this is really 3 over x plus 4 over x squared divided by 1 minus 16 over x squared. Now, whether you go to positive or negative infinity, if you divide a number by x or x squared, each of these is going to go to 0. So this is equal to 0 plus 0 over 1 minus 0. So from this to this step, we've basically evaluated the limit. And this is a number, it's 0 over 1, or simply 0. This means y equals 0 is a horizontal asymptote. And that's it for the first function, f of x. Now, what about asymptotes, either vertical or horizontal, on the function g of x? The approach will be the same. I'll start with vertical asymptotes. I'm first going to check to see where the denominator is equal to 0. That is a possible vertical asymptote. So when does e to the x minus 1 equal 0? Well, that's when e to the x is equal to 1. You can use a natural log to solve this equation. Take the natural log of both sides. The natural log of e to the x is simply x. You're left with the natural log of 1, and the natural log of 1 is simply 0. So actually, is there a vertical asymptote? Possibly. So I'll say this is a possible vertical asymptote at x is equal to 0. To confirm this, we're going to check to see if 0 makes the numerator non-zero. So I will check x equals 0 in the numerator. So that is 3e to the 0 plus 1. Is this a non-zero number? Well, e to the 0 is 1, and that's really just 3 times 1, or 3, plus 1, which is 4, and this is non-zero. I'll state that x equals 0 is a vertical asymptote, in fact, the only one, as x equals 0 makes the denominator 0 and the numerator non-zero. And that's enough. Now to figure out if this thing has any horizontal asymptotes, we're going to use limits at infinity. I'll do that on the next slide. Okay, so we're looking for any horizontal asymptotes of the function g of x. This time, we have to look at the limit as x goes to plus or minus infinity separately. Here's why. Just as a fact, the limit as x goes to infinity of e to the x, well, that's infinite. But the limit as x goes to negative infinity of e to the x is equal to 0. And the reason for this is if you look at a graph of e to the x, it's an exponential function. Towards positive infinity, it tends to infinity, but in the opposite direction, it goes to 0. So if we look at the function g of x itself, we'll first look at the limit as x goes to positive infinity. The function g of x was 3e to the x plus 1 divided by e to the x minus 1. Since we're going to infinity, I'm going to do the same trick that we did in the last example, where I'm going to divide everything by e to the x. So that is, this is 3e to the x divided by e to the x, plus 1 over e to the x, divided by e to the x over e to the x, minus 1 over e to the x. The reason I'm going to do this is because e to the x itself is going to infinity. Remember, we're going to positive infinity. I can cancel these e to the x's. These will remain. So we get, this is the limit as x goes to infinity of, so this is, well, it's really just 3 plus 1 over e to the x divided by 1 minus 1 over e to the x. As x goes to infinity, e to the x goes to infinity, which means these fractions actually go to 0. We can simply evaluate the limit at this point and say, this is 3 plus 0 over 1 minus 0. That's 3 over 1, or just 3. And that is a horizontal asymptote. Y is equal to 3. That's one of them. But we're going to get a different one as we head towards minus infinity. And the reason for this is e to the x doesn't go to infinity, it goes to 0. We won't use a trick like this, but I do think our approach will be fairly simple. So let's do that next. So what about the limit as we go to minus infinity of the same function g of x? So that's 3e to the x plus 1, and then we're dividing by e to the x minus 1. Here, this goes to 0 and this goes to 0. We can simply just put 0 in place of both of those things and evaluate the limit. The reason this works is because we get a number back. So this is equal to 3 times 0, e to the x is going to 0, plus 1, divided by e to the x again, it's going to 0, so 0 minus 1. This is 1 over -1, or simply -1. So there are two horizontal asymptotes. We have y is equal to 3, and also y is equal to -1. In problem 6, we're going to find the derivative of f of x for part A, and we're going to do this by using the limit definition of the derivative. So for this problem, I'm looking for f prime of x, and I'll first state that this is the limit as h goes to 0 of f of x plus h minus f of x all over h. So it's important to know this definition, and you have to know what it says. This says put an x plus h first in place of all the x's. This says subtract the original function itself, and then divide by h. All right, so this is the limit as h goes to 0 of, so f of x plus h is 5 times, well, instead of x, I'll put x plus h squared minus x plus h minus 1. And then I'm going to subtract off the entire function. I want to be really careful here. I'm going to use parentheses because I want to make sure I'm subtracting all of 5x squared minus x minus 1. Essentially, I'm going to distribute the negative, and this is all over h. You might encounter an x plus h squared often, so I'm just going to make a note that x plus h squared, it means x plus h times x plus h. And if you've multiplied these things like these together before, you square the first term, you square the last term, and you get two middle terms multiplied together. This will speed up the process of this computation. So here I have x plus h squared times 5. I'm just going to take this expression and distribute a 5 to every single term. 5x squared plus 10xh plus 5h squared. So my next step will be, this is the limit as h goes to 0 of, again we'll have this giant fraction, 5 times x plus h squared is 5x squared plus 10xh plus 5h squared. I'll distribute the negative to both terms in the next parentheses, which is minus x minus h, and then we have this minus 1. Now, when we distribute the negative into the next parentheses, we get minus 5x squared plus x plus 1. And this would be an easy place to make a mistake. This negative gets multiplied to each term, switching their signs. This is still all divided by h. Now, hopefully a bunch of stuff will cancel, and it does. This 5x squared cancels with this minus 5x squared. What else we have? Oh, we have a minus x and a positive x. And lastly, I think we have a minus 1 and a plus 1. I'll simply write down what is left over. This is the limit as h goes to 0 of, we have 10xh plus 5h squared minus h, all over h. I see that I can factor an h out of the top and cancel it within the denominator. So this is the limit as h goes to 0 of, like I know that h in the bottom should cancel. If you factor out an h, you have 10x plus 5h minus 1 left over. Again, a nice way to check that the factoring we did here is right is by distributing the h to all terms to see if it equals this, and it does. I can now cancel that h. I'll continue this on the next slide, but we're going to be looking at the limit as h goes to 0 of just this expression. So that was the limit as h goes to 0 of, that was 10x plus 5h minus 1. We can use direct substitution here. You'll only put 0 in place of h, so you have 10x plus 5 times 0 minus 1, we're just left with 10x minus 1. This is what the derivative is equal to according to our limit definition. Using the information from part A, I'd like to find the equation of the tangent line to the graph of f at x is equal to 1. So you can use two different formulas for the equation of a line. You can use y is equal to mx plus b, Or if you prefer, you could also use y minus y1 is equal to m times x minus x1. It does not matter which one you use, they both will give you the same answer. So to start with, we figured out that f prime of x was equal to 10x minus 1. And if you want to know the slope of the tangent line to this function at 1, you would use the derivative to figure that out. So the big part for this question is, well, if you want to know what the slope m is equal to, it's the derivative evaluated at 1. So what's the slope? It's equal to f prime of 1. That's 10 times 1 minus 1, which is 9. So the slope is 9. The other thing that you need is a point on your function. That is, you need some x comma y value. Well, we're given that x is equal to 1. And if you want to find the corresponding y value, that's the original function evaluated at 1. The original function was 5x squared minus x minus 1. So y is equal to, okay, so that's 5 minus 2, it's 3. So we have a point. We have 1 for x and 3 for y. So here is my slope, and here is my point. If you use this version of the equation of the line, it's very simple. You'd put 9 in place of m, you'd put 1 in place of x, and 3 in place of this y, and you could simplify it to write an equation like this. Or you can use this point to solve for b. It's pretty much the same thing, whichever way you do it. I will use, I guess, this formula here. So what is the equation of the line that we're looking for? Well, it's y is equal to mx plus b, but we figured out that the slope is 9. The only thing I don't know is, what's b? Well, I know y should be 3 when x is equal to 1. If we simply subtract 9 from both sides, we get negative 6. And therefore we have b. The equation is y is equal to 9x minus 6. This is the equation of the tangent line to the original graph at x is equal to 1. In problem 7, we're asked to find the derivative of the function g using the limit definition. So I think this will be a tricky computation, but let's try it out. G prime of x is equal to the limit as h goes to 0. Here I'm using g's instead of f, but this is g of x plus h minus g of x all over h. If we set this up, this is the limit as h goes to 0 of g of x plus h is 1 divided by the square root of x plus h. And then we're subtracting the function itself, which is the square root of x, and this is all over h. So how do we simplify this thing? I guess for starters, fractions within fractions is not great. So I'm going to multiply the top and the bottom of this main fraction by the least common denominator, which is the square root of x times the square root of x plus h. I have to do that to both the bottom and the top. Now, when I multiply the denominators together, there's really nothing to do. But in the numerators, I would distribute this to both terms. So I'll put some parentheses around this and note that this gets multiplied here and here. All I have to do is note what cancels. This is the limit as h goes to 0 of. When this gets multiplied here, the x plus h's under the square root cancel, and we're left with just the square root of x. Okay, when this gets multiplied here, it's the square root of x that cancels, and we're left with a square root of x plus h. So it'll be minus the square root of x plus h, all divided by h times the square root of x times the square root of x plus h, this. All right, the ultimate goal is probably to cancel this h here, because that's creating the division by 0. Here I have a difference with two different types of square roots. Here's where you'd want to use the conjugate to help figure out what goes next. The conjugate is the square root of x plus the square root of x plus h. I'll put that over here, one in the numerator and one in the denominator. Like I said, this is going to be kind of a mess, but it's going to be the square root of x plus the square root of x plus h. This is divided by the same exact thing. It has to be, because if this is equal to this, the whole fraction is equal to 1, and multiplying by 1 doesn't change what we start with. Just be careful. We're going to have to distribute. In the denominator, I won't distribute. I'm not going to distribute this stuff into here because I want to leave this h all by itself. So in my next step, this is the limit as h goes to 0 of, I'll write the denominator, it's going to be a lot, but we have h, the square root of x, the square root of x plus h, and then the square root of x plus the square root of x plus h. In the numerator, we'll have root x times root x, which is nice. It actually just gives us x. We've used this trick before in this review. You multiply this to this, and you get positive root x times root x plus h. But then when you multiply this here, you get the same thing, but with a negative. The two middle terms cancel. The only other thing you get is this multiplied to this. It'll be negative, you'll get minus. And since this is the same as this, you're squaring the square root of x plus h, which means you're just left with x plus h. Just be careful to put it in parentheses because you want to make sure that this negative gets multiplied to the whole thing. On the next slide, I'll distribute this negative into the parentheses, cancel this h, and then evaluate the limit. If I distribute the negative, we'll have the limit as h goes to 0 of, so it's really x minus h, it's supposed to be an h. In the denominator, we have h, the square of x, the square root of x plus h, then multiplied by the square of x plus the square of x plus h. All that stuff, a lot of stuff. In the top, we have a negative h left over, and it's been a long way to go here, but the good news is you can now cancel a factor of h. This cancels with that, and technically we have negative 1 left over. This is the limit as h goes to 0 of, that's negative 1, divided by root x plus h, and then root x plus h. We're basically done, even though it might not look like it. We can now put 0 in place of h, and we'll have an answer. This limit will be defined. It's going to be negative 1 in the top. In the denominator, if you put a 0 in place of all the h's, you get root x multiplied by another root x. You don't need the plus 0. In parentheses, you'll have root x plus root x. Wow. Negative 1 over, okay, root x times root x is simply x, and then root x plus root x is 2 root x. I think it's probably fine to leave it just like this. This is negative 1 divided by 2 times, I'll say x root x. I'm sure this could be simplified further. I think it is completely fine to write this as our function. In problem 8, we'd like to use this graph to evaluate a few functions and limits. And we'll also explain when they do not exist if that happens. So to start with, I want to figure out the value of the function at negative 1. This is not a limit, but this is asking at negative 1, what is the value of the function itself? That's going to be this closed circle here, which is at y is equal to 0. So this first one's simply 0. Likewise, what is f of 2? Well, the value of the function is not defined here. It's an open circle, but it is defined here, which is a y value of 1. So the first two are just, what does the function equal? The next are going to be limits. So what is the limit as x approaches negative 1, but from the left side? Here we're talking about this portion of the function, and it looks like it is approaching this open circle, which is at 2. So this is 2. What about if we approach negative 1 from the right side? That means we're getting closer and closer to this y value, which is 1. Remember, when we deal with the limit as opposed to the function, we're asking, where is it going? We're not asking, what does the function actually equal at negative 1? So here we go. The limit at negative 1 from the left was 2. From the right, it was 1. Can we define the limit as we approach -1 overall? And the answer is no. It does not exist because the limits as x approaches -1 from the left of our function, it's not equal to the limit as x approaches -1 from the right. No good. We'll now consider the limit as we approach 2 from the left, the right, and all together. As we approach 2 from the left, it looks like the function is headed towards this open circle, which is at -2. In fact, that's the value of the function. What about as we approach 2 from the right side? It's also going to -2, so this is -2. Can we say the limit at 2 exists even though the function equals 1? It doesn't matter what the function equals here. All that matters is as you approach 2 from the left and the right, we're always heading towards -2, so this exists and is equal to -2 as well.